Hello and welcome to this series of lectures on FFT algorithms. In this lecture, we will be talking about decimation in time and decimation in frequency FFT algorithms, which are very popular algorithms for computing discrete Fourier transform. My name is Mudassar Naikwadi. I am from Electrical Engineering Department at NB Navle Sihamgarh College of Engineering. Before going to the algorithms, let us try to understand what is fast Fourier transform. We have seen that discrete Fourier transform is a transform which is used to compute the frequency domain representation of discrete time aperiodic signals. It is the sampled version of DTFT, that is discrete time Fourier transform. Why do we go from discrete time Fourier transform to discrete Fourier transform? The reason is DTFT is continuous in nature, hence the continuous data we cannot store it on a computer. Therefore, we sample the DTFT in order to get a discrete Fourier transform. So discrete Fourier transform is discrete in nature. So it can be stored on a computer, manipulated on a computer, and processed. So that's why DFT is a very important tool for analyzing the discrete time aperiodic signals in the frequency domain. Now, to compute the normal DFT, that is for direct evaluation of DFT, we require for direct evaluation of DFT, we require a lot of computations. Now, why we require a lot of computations? Because in this DFT equation, if you see, k varies from 0 to n minus 1, and n also varies from 0 to n minus 1. And this twiddle factor, which is e raised to minus j theta, it is splitted into cos and sine. Okay, that is trigonometric values. So if you see the number of computations that is required, okay, the number of computations that is required for direct computation of DFT will be very large. Now this will increase exponentially with the value of n. So as the value of n increases, so normally this n is 4, it is 8, it is 16, it is 32, and so on. So it is normally a multiple of 4. So if you see this, the number of complex multiplication we require is n square, number of complex addition required is n into n minus 1, and so on and so forth. So that's why if as this n increases, the number of computations increases exponentially. You can imagine that when n goes to certain value, say 64, then 64 raised to 2, that is 64 into 64, that is so huge number of computations, and normally the practical value of n is 1024. So 1024 into 1024, that is a very huge number. That's why the direct computation of DFT is very difficult and it requires a lot of computations. So there has to be certain algorithm in order to reduce this number of calculations. And in order to reduce this number of calculations, we have an algorithm which is called as the fast Fourier transform algorithm. So this fast Fourier transform algorithms is of two types. One is called as a decimation in time frequency decimation in time FFT algorithm, and another is called as a decimation in frequency FFT algorithm. So these two algorithms we are going to use for computing DFT. So remember that this FFT is not a transform. It is just a set of algorithms, and the use of that algorithm is to compute DFT. So DFT is our main transform, and to compute the DFT, we make use of these FFT algorithms, and we will see what how this FFT algorithm is used. What are the steps involved in these FFT algorithms. Now, how to reduce the number of calculations? That is the question. Okay, so the reason is that we can reduce the number of computations involved in direct computation of DFT because the twiddle factor which is there. Now in this equation, this e raised to j term is what is called as a twiddle factor we had seen in the last lecture. So this twiddle factor helps us to reduce the computations because this twiddle factor exhibits two property. One is called as a symmetry property and another is called as a periodicity property. So we had seen that there is no need of computing so many twiddle factors. Even if you compute 4 twiddle factors, it is sufficient for 8-point DFT because another 4 will be repeated because due to periodicity property. And here also we need not compute the values of all the 4 DFTs because by using the symmetry property we say that there is only a difference in sign of the opposite values. So this shows that it is not necessary to compute the twiddle factor values so many times. Okay, if it is a 8-point DFT, if we compute only the four values, it is sufficient to get all the remaining values. So this property of twiddle factor helps us reduce the number of computations required for this DFT, and hence the computations become faster, and this algorithms works very fast. That's why it is called as fast Fourier transform algorithm, FFT. So fast Fourier transform algorithm, because the number of computations are less, so the speed is more. Now, depending upon how the sequences are divided, whether they are decimated in time or whether they are decimated in frequency, we have two types of FFT algorithms. One is called as decimation in time FFT algorithm, decimation in frequency FFT algorithm. What is the meaning of decimation? To decimate means to divide. So if you are given 8 samples, then we decimate into 4 and 4. So this 4 and 4 we can again decimate or divide into 2 and 2, and so on. So this is called as a decimation. So when you go on dividing the number of samples, so when you divide the number of samples in the time domain, it becomes decimation in time FFT algorithm, and when you decimate the samples in the frequency domain, it is called decimation in frequency FFT algorithm. So these two algorithms are very important algorithms for computing the DFT. Now let us see the first algorithm, which we call as the decimation in time fast Fourier transform algorithm. Now we have to understand the steps involved in computing the DIT FFT algorithm. So we have to note down the steps that are used for computing this DIT FFT algorithm. Step number 1 is, once we are given the sequence, suppose we are considering a 8-point sequence. So the sequence given is 0, 1, 2, 3, 4, 5, 6, 7. So these are the samples of the sequence. So the sequences are represented by x of 0. So first sample is x of 0, second sample is x of 1, and so on. So these are the 8 samples. Okay. So now these 8 samples are given. So we are considering 8-point DFT. So if you want to compute a 8-point DFT, so our n value is n, 8. Okay. So to compute the 8-point DFT, here n is equal to 8. So for n is equal to 8, to compute the 8-point DFT, how to compute the 8-point DFT? First we have to consider, now since n is equal to 8, there will be 8 samples. So the samples are from x of 0 to x of 7. Since the index starts from 0, we have up to 7. So these are the 8 samples that are given. Now what we have to do, we have to go on decimating these samples such that we get the sequence in this order, that is 0, 4, 2, 6, 1, 5, 3, 7. So what we have to do, we have to separate the even and odd samples first. So from the given samples, first let us separate the even samples. So 0, 2, 4 and 6. These are our even samples. And again, if we divide this again, if we consider only the even samples here in this case, then we will get 0, 4, then 2 and then 6. That's why we get here 0, 4, 2 and 6. Similarly, next what we do is we decimate the odd samples. So what are the odd samples here? 1, 3, 5 and 7. Now again, if we decimate this 1, 3, 5, 7, so first we will get first 1, 5, 3 and then 7. That's why this is 1, 5, 3 and 7. Now when we will solve the numerical on DIT FFT, how this decimation is taking place, that we will understand, that will become clear. But now the first step, you remember that whenever the sequence is given, in case of decimation in time FFT algorithm, we have to first decimate the given sequence into even and odd samples, again into even and odd samples, so that we get the samples in the bit reversed order. So this change in the order of the sequence is called as a bit reversed order. Okay, so what is the meaning of bit reversed order? We will see in the next session, in the next lecture. So remember the first step of decimation, and this, since this decimation is in time domain,